Okay, so we're going to continue our run through the 12 basic functions. Actually, we have 1, 2, 3, 4. We only have 5 left. So let's go ahead and take a look at it. The first one we're going to take a look at is y is equal to sine x. Y equals sine x goes like this. Okay, y is equal to sine x. What is the definition of sine x? What is the definition of a sine? What is it? Do you guys remember this stuff from SOHCAHTOA. What does that mean?
So that means sine is opposite over hypotenuse.
Okay, so sine is opposite over hypotenuse, right? So it's opposite over hypotenuse, okay? Which means that by definition, since an opposite is along with the adjacent, the two legs of a right triangle, correct? So if I had a triangle that looked like this would be the hypotenuse, and this is the angle, then this guy here would be the opposite, and this guy here would be the adjacent. There's no way that the opposite is ever greater than the hypotenuse, correct? Because the relationship that we understand here is that the hypotenuse squared is equal to the adjacent squared, correct? Right? That's Pythagorean theorem, right? So, therefore, since the opposite can never be greater than the hypotenuse, sine can never be greater than 1. Okay? Same thing with the cosine, right? Cosine is just the adjacent over the hypotenuse, but again, it's never going to be greater than 1 because of that. That's the limitation. Okay? All right. That's just some background story there. So y equals sine x. What is the domain? Huh? All reals. Good. What about the range? It is what here?
2 and 2.
1 and negative. We just went over this. It can't be greater than 1, right?
Mm-hmm.
Okay. So the range is going to be between -1 and 1. Therefore, it is bounded upper and lower. Bounded upper by 1, lower by -1. Does that make sense? Symmetry-wise, what do we have? Is it symmetrical? Across what? The origin is symmetrical across the origin. Therefore, it is a odd function. Okay, boundedness, we're good. Any asymptotes? No asymptotes, right? I have many local mins, local maxes, right? Which actually happen to be global max or min too, because they're all kind of the same, right? And local mins, local maxes. Okay. Is there anything else we need to talk about? Increasing or decreasing? Sometimes increasing, sometimes decreasing, increasing, decreasing, back and forth, right? Okay, that's it. We're good. Cosine. I'm going to draw the cosine graph right on top of this. Because it looks kind of similar, but it really isn't. Okay, it's the blue one. It's the blue one. Domain and range are exactly the same, correct? Because, so we're doing cosine x, okay? Because the domain, again, is all real x's, right? There's nothing that says anything we can't be. And there's the ranges, again, is between -1 and 1. Bounded upper by 1, bounded lower by -1, right? Okay. So this guy, like we said, would be adjacent now. But still, that's why we have the bounded by 1 and -1 thing. The negative part, we will talk about that second semester, okay, where this negative comes from. Okay, we'll do that in the trigonometry part. There we go. So we got that, and it's an okay. So the cosine function is not an odd function. Cosine function is a even function because it is across the y-axis, correct? So the y equals cosine would be an even function. All right. Okay, we're good with that? Are there any questions or anything I need to talk about besides that? No? Okay, let's go over. Okay, so now we're going to talk about the absolute value function. Absolute value function, if you remember correctly, the function looks like this. Y is equal to that. Domain and range. Riley, domain. All reals, very good. Range. Greater than or equal to 0, right? Up this way. Anything else I need to know about it? Huh? It's an even function because it is across the y-axis, right? It's symmetrical across the y-axis. All right. Anything else? Bounded below. Very good. Sometimes decreasing when x is less than 0. When x is greater than 0, it becomes an increasing function, right? Decreasing, increasing, right? That's it. And then we'll do the my favorite function. And that is the logistic function. Logistic function looks like so it goes like this. This is the logistic function, and we will touch on this later on. Looks like that. Okay. So let's go ahead and graph this function. I want to make sure you guys can graph this function. Let's go ahead and graph it. Raise your hand if you got this. You got the graph? Go ahead and show me. Go ahead and raise it. Here, raise your hand so I can verify it. You can't get it? You got it. You got it. You just need to change the window. Same thing for you. Change the window. Change the window also.
What's your dimensions at?
Number 2, yes. Go from
Yeah.
0 to
You might want to change that to like 10. I taught you how to do the fraction bar. Get a flea.
0,
Out of
x,
space.
x min of 0. I do -1. -1, 2, 3. X. I mean y-wise, not x. Y.
Is this?
X, I would do -10 plus 10. Yeah. Widen your window too, okay? All right. Zoe and Zoe, did you get it?
I got an error.
No. Who got an error?
I did syntax error.
Somebody help him. Riley, did you get it?
I got it right.
Help Zoe, please.
Yeah, mine's just like this.
Yeah, that's what mine's put the other way.
No, yours was the opposite.
What was the y-intercept that you find, Carter?
It's just because the window's bad, but it's what.
The y-intercept.
Yeah, this is right.
No, we just got
1/2. Everybody else get 1/2? 1/2, okay. The reason why you got 1/2 is this. When x equals to 0, that's my y-intercept, correct? When x equals to 0, x equals to 0, e to the 0 is what?
One is.
It's 1, right? Anything to the 0 power is 1. So 1 over 1 plus 1, 1/2, correct? Does that make sense? Okay. What is special about this graph? Is it symmetric?
To the negative x power.
Oh.
Is it symmetric?
Yeah.
Yeah, it is?
Y-axis.
Across what?
Y-axis.
Oh no.
What kind of y-axis is symmetric across? I don't think so. Because if I flip this over, I'm going to get something like this.
Oh.
Right? So it's not symmetric across the y-axis. It's not symmetric across the origin. So it's neither even nor odd. Does it have asymptotes? I have horizontal asymptotes, right? As it's going this way, the horizontal asymptote is 0. As it's going this way, the asymptote is what? 1.
Yes.
1, right? Because as x goes all the way out to infinity, what's happening to this number?
Increasing.
Is it increasing? E to the negative 1 billion? E to the x is increasing, but e to the negative x is equal to 1 over e to the x, correct? So as x goes really, really large, this guy goes to 0, correct? 1 over 1, therefore your right-hand side asymptote would be 1. So it has 2 horizontal asymptotes depending on which way you're going, right? You see that? There are many, many, many things in real life that you use this function to model what's happening, such as COVID, such as the spread of a rumor, right? If I started a rumor at day 1, right, in Blanchett, how many people are Blanchett? 400, right? 400 students. How many people will know at the end? Because at the very, very end, everybody's going to know. Correct? So it's trying to get to what? 400, right?
Mhm.
So it'll go like this. So there's a huge, everybody's, this is the really, right, sensational whatever, I don't know, and then it kind of just dies off after that. Right? Okay. Right. So those are the type of things that we can model with this. If I opened up a new national park full of, and I introduced wolves, gray wolves. Same thing. Right? It's going to go all the way up to a point where the park will only sustain so many wolves, right? That kind of stuff. So there are many, many things that you can use in real life that follows this, which is why it's a fun thing to know. Okay, so we'll talk about that later on. Okay, then the last one. Okay, so it was bounded by 1 and 0, right? Lower bound by 0, upper bound by 1. No symmetry. Oh, Ben's favorite. It's an increasing function, right? It increases the entire time. Okay, all right. Right. Now the last one, which is the one that I really don't enjoy. It's not even really a function. It really has no usage. It's called the integer function, or the greatest integer function. Greatest integer function. So if I have a number, what is the greatest integer for that number is what we're asking. Right? So if I start with 0, it's still going to be 0, 0.1, 0.2, 0.3. It's still 0 until I get to 1, correct? So once I hit 1.0000000, it jumps to 1. And then it goes all the way up to almost to 2, and then it jumps again to 2. Right? So in the meantime, these are open dots, correct? So I have discontinuities all over the place, right? Right? Yeah, it's not a fun function. Okay? It is, is this an increase? Yes, it's an increasing function, I guess, to a point, right? Not increasing or decreasing, all of a sudden increased. Not increasing or decreasing, all then suddenly increased, right? Blah, 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 it goes on and on. Is it local max or min? Not really, because it goes on forever and ever, right? Is there symmetry? Not really, even though there is on the bottom part. Gonna go like this. Okay. It's still not even symmetrical across the origin, so there's no symmetry. And no asymptotes. It's a stupid function. I don't enjoy it. I don't like it. Anyway, so that's that. Blah, blah, blah. Looking for domains. So let's look at the questions here. Make sure we've talked of everything. The only thing that we did not talk about is on page 104. There is a piecewise function. So let's look at example number 7. Let's do example number 7. We'll quickly go over that. Example number 7. Using basic function notation, that appears to be so. Using basic function notation, construct a piecewise function for the graph that is shown in figure 1.52. In 1.52, I have a graph that looks like this. So all this is saying is that on the left-hand side, I have y is equal to x squared. So on the left-hand side, on the right-hand side, what do I have? Which function is this? Square root of x. Square root of x. When x is greater than or equal to 0. Actually, well, what about when it's equal? It doesn't really matter which side it's on because either way it's 0, correct? All right. So in other words, is this a continuous function? Can I draw this function without lifting my pen?
Yes.
Yes. So it's a continuous function, correct? All right. Just realize that there is a thing called piecewise function and what it looks like, okay? Not do all piecewise functions look like this? No. Right? You can come up with a gazillion different kinds of piecewise functions. Are all piecewise functions continuous? No. Right? I can draw a function that looks like, I don't know, like that. It's not continuous, right? It's a piecewise function because at this point there's a distinct different function, right? Okay. All right. Okay, we are done. I am done with 1.3.